So I guess we should get started. Thank you everybody for coming to beautiful Santa Barbara. Thankfully, we were able to secure every single person here is able to have a single office with an ocean view. I had to work really hard to get that, but if you can make it there, you will be awarded with such an office. But in this weird time where we have been apart from each other for so long, we thought it would be a great idea to have something like this where most people would be able to attend and get back to talking to each other in a more formal or more formal and informal environment. And we have a good. We only have 2 days, so we have 8 speakers. 8 very good speakers, and also lots of time for discussion and questions after each talk. So during the talk, unless it's like a really pressing question that you think needs to be asked, you can ask it. But normally we're going to just hold questions till after the talks because we have plenty of time for that, and hoping for lots of interaction. So I hope you brought your anything you want to discuss or that'd be great to talk about here. And so our first speaker is one of the lead scientists of EHT, who is just coming off a fresh press release, which I'm assuming was quite hectic, and I had no idea that this was going to be happening right before the conference, so I apologize for that, Feryal. But it's Feryal Ozel, who will be talking about particle heating and acceleration in black hole accretion flows, just overviewing a lot of the recent work that's been happening, and telling us all about that. So take it away, Feryal.
Thank you very much, Sean, and all the organizers. Thank you for inviting me to kick off this conference. So indeed, I would like to give you an overview of what's been happening with our understanding of what particles do, what their energy distribution functions are like in black hole accretion flows. And in my title, I'm referring to both heating and acceleration. But I know that Bart after me is going to talk a little bit more about acceleration. So I'm going to try and divide my talk between what we understand about how particles are heated, how they're accelerated, whether they thermalize, and equally on what the observational signatures are. So hopefully you can see my screen okay. Can you hear me okay? All good. All right. So somehow I lost all my controls, but okay, this is working. So let's put this in context as far as plasmas go. Why low density accretion flows or low luminosity accretion flows, where the gas density in the accretion torus disk funnel is low, and it is also a magnetized plasma, obviously. Why these are unique, and what are the specific challenges that follow from that uniqueness of the parameter space. So to put things in context, what I have here is typical, what I call typical length scales for Sagittarius A star in centimeters. And the various quantities we're looking at are the gravitational radius, RG, that sets, of course, the scale of the entire flow. The electron gyro radius, which is connected to how electrons get heated and their micromotions. The ion gyro radius, the electron mean free path, and the ion mean free path to collisions. And I've divided the flow into 3 regions: disk, funnel, and outer. So using characteristic values for density, magnetic fields for these various regions that we see in GRMHD simulations, the takeaway point here is that the electron gyro radius is of the order of tens of centimeters, whereas the gravitational radius is a factor of maybe 10 to the 10 higher than that. And the mean free paths are a factor of 10 to the 15 higher than that. So when we say collisionless plasmas, this is what we are referring to, that we can't rely on collisions that we all love in our equilibrium concepts to equalize things, equalize energy distributions, equalize and turn everything into a beautiful Maxwell-Boltzmann distribution. So the other thing here is, of course, is the separation of scales. How do you, in a computational calculation, simultaneously account for hundreds or thousands of gravitational radii where you're interested in the properties of the flow, and the electron gyroradius where the pumping of energy to the electrons happen. So these very large separation of scales, both collisionless and the flow itself is large, pose unique challenges for our case. Let's also look at typical time scales to set the scene. What I have here is the electron-proton thermalization time scale on the left. There is a similar expression for electron-electron, which is even a longer time scale. And if you can focus a little bit for a minute on this expression here, this is the viscosity alpha, this is the dimensionless electron temperature theta, normalized to MEC squared. This is the mass of the black hole. This is the mass accretion rate onto the black hole in Eddington units. So we are quite far from that in Sgr A and M87 and nearby low luminosity accretion flows. And this is the radial dependence. And this is the accretion time scale in those same parameters. What you will notice is that the mR to the 3/2 is the same in both cases. And the coefficient is roughly similar in both cases, except that for it to be the same, we would have to be near Eddington. Even at near Eddington, the electron-proton thermalization time scale would be a factor of 10 higher than the accretion time scale. But we are way below that. So we don't have enough time for the thermalization, this thermal relaxation to actually happen and expect Maxwell-Boltzmann distribution. As a result, what that means is particle heating is challenging to simulate, on accretion flow models. And even when we don't have active acceleration processes, what we associate with energetic Fermi processes or other types of acceleration, we expect the presence of non-thermal particle energy distributions. That is the segue into, well, how about particle acceleration? Do we expect that to happen in these environments? And here I have a little graphic from a GRMHD simulation. This is meant to represent the inner accretion flow. This is radius in units of gravitational radii. Again, same here. This is the vertical direction of the disk. So this is somewhere in the inner flow of a GRMHD simulation. Of course, our simulations are ideal, so we don't really allow for dissipation to happen other than numerical dissipation. But that doesn't mean that we can't go and look at would there have been dissipative processes if we allowed non-ideal MHD. And what we see here is rapid flipping in the magnetic field in the phi direction. Rapid meaning over short excuse me, over short length scales, we see that the sign of the magnetic field flips, and there are large current sheets that are associated with these naturally. So if we were allowing reconnection to happen, if we were allowing non-ideal processes to happen, these would have been prime locations for acceleration of particles. So magnetic reconnection could lead to additional acceleration processes in addition to how electrons and protons get heated. Excuse me. For those of you who didn't hear it in the beginning, I have valley fever, so it's ongoing. Okay, so let's go ahead and characterize these acceleration regions. And of course, being plasma astrophysicists, there are certain parameters that we are interested in that help us understand how relativistic a flow is, how magnetically dominated a flow is. And these useful parameters are magnetization, so energy density in the magnetic field, This is normalized to the enthalpy, so mass density plus the internal energy. This is our parameter sigma. And we also use a plasma beta, which is the ratio of the thermal energy to the magnetic energy. And the lower this value, the more magnetically dominated we are in the flow. For low luminosity accretion flows, again, when we look at our simulations, what we find is that we are right in the transrelativistic regime. So sigma is between about 0.1 and 10. And betas can be quite low, 0.001 up to 10. And this is going to play a role. What value beta has is going to play a role in both heating and acceleration, as you will see. Okay, so why do we care? I mean, I can, just from the faces that I see on this conference, on this call, I know that you care because you love physics and you want to understand, well, how does this collisionless magnetically dominated plasma work? But really, why do we care? I mean, what are the connections to observables? How is this going to affect what gravity observes, what EHT observes, what Chandra observes, etc.? And as an example, I'm showing something from a paper that I wrote in 2000, one of the first systematic explorations of, well, if the energy distribution wasn't thermal and we had a power law tail, pretty phenomenological, what would the effect be? So here is the dots here are the data on Sagittarius A star. It's broadband spectrum. Of course, I'm cutting it off in the radio here. And these are the infrared upper limits at the time. And these are a fraction of energy going into a power law tail and the power law index of that distribution. So what you're seeing here is that the dashed line would have been the thermal spectrum without the presence of this sub-percent level of energy going into a non-thermal tail, which I just argued should be there. And what it does is, in the longer wavelengths, in a long wavelength radio, it changes the source function. The ability to emit is above a Planck function, so it modifies the spectrum. And of course, depending on the power law index, in the infrared as well, the expected emission simply from synchrotron. This doesn't even take into account the effect of inverse Compton, etc. on the other wavelengths. It would be different. So first, we would see the effect on the spectrum. How relativistic do they need to be to make a difference? So when we go and talk about, for example, in a little bit magnetic reconnection, are we talking about Lorentz factors of 1,000,000 or more? Like, is that what we're talking about when we say a non-thermal tail? No, again, this is from the same paper, identifying the ranges of Lorentz factors that play a role as a function of frequency in modifying the spectrum. So what this shows you, this is log of the Lorentz factor. What this shows you is that really mildly relativistic particles give rise to that excess emission in the radio, and also going towards the infrared. We are talking about Lorentz factors of 100 to 1,000 that really make the flow shine in a very different way. So that's why we are interested in being able to model these correctly and being able to understand what the relaxation processes are. Again, from the same paper, because it was just the overall study of what are the effect of unobservables of non-thermal particles. This is the effect of the particle distribution function on the image size. We were, in the year 2000, we were just starting to think about interferometric measurements of black hole inner flows, and which led to the EHD. And of course, the Thomas Crickbaum and Fred Lowe's measurements had happened just a couple years prior. and we were heading towards the horizon of the black hole. So this is my plot from that time, the full width half max of the accretion flow in units of Schwarzschild radii as a function of frequency, basically asking ourselves, where is the photosphere and at what point does an observer see down to the horizon? Because of the particular dependencies of synchrotron emissivity on the flow parameters, basically at long wavelength radio, you see a large blob and it shrinks and the horizon becomes apparent right around 1.3 millimeter, 1 millimeter, which is obviously where we're doing the HD measurements. So at that time, with the simplistic model, what we had showed is that the hybrid, the presence of the non-thermal tail, affects the image size at long wavelengths, but its effect disappears. With those simple parameters, its effect disappears at these shorter wavelengths. But there have been beautiful investigations since. This is from a paper that Jason and Elliot wrote with I think an undergraduate at the time, a more sophisticated 3D exploration of the effect of non-thermal electrons on the image. And what they found is that indeed a small fraction of parallel electrons changes the image, and it produces a diffuse halo of emission. So this is 3D fully rendered with ray tracing, etc. And what I think how this relates to the previous work is that what you'll notice is that the full width half max roughly remains constant. So the brightest part of the emission stays constant, but even a very small fraction of non-thermal electrons introduces this halo, which we could resolve in our imaging experiments. Now, that was the second observable. I talked about spectra, I talked about imaging. How about variability? Well, how does this manifest itself in time-dependent studies of Sgr and other low luminosity black holes? As we all probably know, and we're going to hear more tomorrow, Sgr shows persistent variability and flaring in all wave bands. This is from Witzel's paper in 2018, Spitzer and Keck data. What we are seeing is that of the order of timescale of minutes, Sagittarius A star shows variability and flux of excursions that are quite significant. So factors of at least 5 or so in flux in the infrared. So how do we understand this? I mean, we know that accretion flows are turbulent. That's why they accrete in the first place. But does just natural turbulent timescales show both the timescale, just the levels of natural turbulence? Does it account for both the timescale and the magnitude of the variability that we see? This is now in Chandra, with Chandra in the X-rays. So this is from Joey Nielsen's paper about 7 years ago. Same thing, same story. In the X-rays, there's also rapid variability. The difference is that the flares, what are identified as flares, not just the fluctuations, can be very significant. So the count rate can go up by a factor of 100 over a very short time scale. So even though, of course, Chandra doesn't resolve the inner accretion flow, it is actually focusing on a larger region just by its ability to resolve the galactic center. What we're seeing is very rapid flaring events and recurrent, some of which are coincident with the IR flares. So every IR flare has an X-ray counterpart, but not vice versa. In a study around that time, we had looked at how GRMHD models with a thermal distribution of electrons behave as far as their variability in multiple wavebands. So what you're seeing here are light curves that are rendered from a GRMHD simulation in the radio, 1.3 millimeter, infrared and X-ray. Detrended means we took away the overall decline in the flux as the accretion proceeded, because matter is actually being lost from the accretion domain, or from the simulation domain. And this is just some example. What you're seeing is that in the infrared, indeed, just the normal fluctuations in density and temperature and magnetic field can cause the variability that we see, but it does not account for the X-ray variability. But hold your thoughts. There is a Sean has a later result that I will refer to that is a little different than this. But regardless, at the time we said it does not account for X-ray variability or flaring, but it can account for some infrared variability. So what we did with my former student David Ball is we said, okay, let's now add a population of non-thermal electrons in the flow based on where we think they might appear, again with a prescribed fraction and a prescribed power law index. And there what we found is that the indeed, not only does this presence of non-thermal electrons produce even more IR variability, but now it also produces the flaring of the type that we see in the Chandra data. So we showed the correspondence between X-rays and infrared, and the flux excursions resembled the Chandra data a lot more. Okay, so those were my, not motivation slides, but the slides that connect the microphysics to the observables that we might all care about. And hopefully you're left with the feeling that, yes, this is a worthwhile problem to understand, not just from the physics point of view, but because now we're doing all these high resolution, high time resolution, high spatial resolution, etc. experiments, and we really better understand how the emission occurs and is different due to the electron energy distribution. So moving from just Planckian distributions and prescribed power law tales, how do we get better at understanding how the heating in the plasma happens? So this is a plot and an expression that I'm showing from Sean's papers in 2015 and 2017 that shows the heating rate of the protons versus the electrons. And the key characteristic of this model is that the heating occurs in a way that depends on that plasma beta that I had defined earlier, that at low beta, the electrons get more of the heating. So this is an attempt using different MHD dissipation calculations to capture how we might be able to go about understanding that dissipation of MHD turbulence at these different scales as a function of plasma beta, and putting it into our GRMHD calculations. So if we take a heating prescription that is of this type, where electrons receive more of the heating at low beta, and we now look at what the spectrum does. This is nu L nu as a function of frequency, again, showing now a wider range from the radio to the X-rays. What they found is that this more sophisticated, physically motivated heating indeed changes the spectrum, and it also causes variability in X-rays That is more than what we had seen in that 2015 study. But let me also mention that inverse Compton scattering is included here, whereas it was not in the other one. So it's a combined effect of a different heating prescription and the taking into account the effect of inverse Compton scattering of those synchrotron photons and how that contributes to the X-ray emission. So the gray band here is basically the range of fluxes that one gets, and I forgot to mention, all of these models also take into account the role of conduction. So we are also trying to understand how more of the energy equilibration might happen due to conduction rather than collisions. So that makes a small difference, as you can see, between the red curve and the blue dashed curve. But the range of fluxes that we see, even with a more sophisticated prescription, does not reach the flaring levels that we see in the X-rays. So back to the point of heating is important, understanding how energy is dissipated is important, but we still need an additional physics to understand some of what we're seeing. This is now, I mean, I already mentioned it when I was showing the spectrum, but here is also the light curve that one expects in the near infrared X-ray and compared to the quiescent X-rays. As you can see, quiescent X-rays are just a flat line here, and the near IR and X-ray flaring is coupled both through that good processes and because of where the energy is in the flow. As I said, we need a different process to understand the flaring events. So in this last part of my talk, I want to mention a little bit of the particle acceleration in reconnection work that we've been doing. I know Bart after me is going to get into more details. I'm hoping that whatever I leave out, you're going to cover, Bart. So this is again work that I have done with my former graduate student David Ball and our collaborator Lorenzo Cironi at Columbia. And what we had done, and what I tried to convey to you earlier, is that GRMHD simulations really guide us into the parameter regime that we should be studying, as far as what are the sigmas, what are the plasma betas, where are the current sheets, and what types of densities, etc., we can expect. So what we're doing here is, because of that separation of scales problem that I was alluding to earlier, we're saying, okay, let's use the large-scale simulations to guide us to the right microparameter space, but then set up small particle in cell, small as in spatially small, but highly resolved particle in cell simulations to understand what happens to those current sheets and what happens to the particles as a result of reconnection in those current sheets. So this PIC stands for particle in cell. The way we set this up, as these graphics also show, is that there is a Harris current sheet with this particular mathematical expression. What that does is, of course, reverses the direction of the magnetic field. So magnetic field lines going in this way here, and magnetic field lines going in this way here. In this particular case, we were able to employ equal, we use equal proton and electron temperatures, and we were able to employ the true mass ratio. So instead of doing a paired plasma, we were actually able to have a different mass for the ions, which is correct for the protons. These particular simulations don't have a guide field. What that means is that in a realistic situation, you would also have a component, you could also have a component of the magnetic field in a direction that's perpendicular to what you're studying with your Harris sheet. but these particular simulations ignore that. Later on, we did a set that has the guide fields. Okay, so this is the initial setup of the Harris sheet, and initially it's an equilibrium. Excuse me. We achieve pressure equilibrium initially by including a hot and overdense population of particles in the current sheet, and we trigger reconnection in these simulations, meaning we remove that pressure support and allow the current sheet to collapse and reconnect. There are other approaches to this, allowing for it to develop naturally, and qualitatively it gives similar results, but the evolution of the current sheet when the reconnection is triggered versus it develops it develops naturally is different in terms of the number of X points that form, meaning the collapsed points in the current sheet where the non-ideal electric fields form. The numbers are different. So each computational cell is initialized with anywhere from 4 to 6 particles, and the electron skin depth is resolved with at least 3 particles in this setup. I don't know if this is going to play in a way that you can see, but this is a simulation that I wanted to show you as far as an evolution for a low beta case, and sigma of 3, technical difficulties. What happened to my movie here? Oh, okay, it's playing. So what happens is that once reconnection is triggered, there is a primary X point, and that's due to the tearing mode, the primary tearing mode, and very quickly, lots of small blobs of plasma that we call plasmoids form, and they move in the X direction at roughly the alphane velocity. So the boundary is periodic in the X direction here, so you're seeing a little bit of the effect of that. But over time, these plasmoids merge and also go through a secondary tearing mode. So multiple X points will form, especially in the low beta simulations, like the one that I'm showing you here. There is a formation of islands and large numbers of islands and X points. This is important. I'm trying to describe it to you in words right now, because what we will find is that this is directly related to how the electrons get accelerated in these peak simulations. So what happens to individual particles and their distribution as that reconnection proceeds? So what we have here is the electron and proton energy distributions. This is Lorentz factor -1 in the denominator as a function of time. So it evolves from this lightest green here to the red at the end of the simulation. Again, for a low beta, and this is now sigma of 0.3. The previous movie that I showed you was for sigma of 3. What is happening, as you can see, is that the electron distribution very rapidly at these low beta values acquires a non-thermal characteristic. So energy is injected into particles rather quickly. So even in the earliest time steps, it has evolved from, this would have been the thermal distribution for electrons. This is now at the earliest time step, and it acquires a shape that for ease we could describe as a power law. obviously it is more complicated, and at high beta, actually, we see a secondary peak forming, a softer but more distinct peak forming at high Lorentz factors. But at these low beta cases, the electrons indeed get their energy from this reconnecting magnetic field and rapidly acquire a non-thermal energy distribution. And so do the protons here. Why does it happen? I mean, is it a Fermi type process? Is it just bouncing around between these islands, or is there something else going on? So in order to study that, we also looked at tracer particles, and we did a whole bunch of other tests that I won't be able to get into. And what this animation is going to show you from an actual calculation is that electrons get most of their energy when they go through X points. So it is actually going through the regions of non-ideal electric field that is associated with the reconnecting magnetic field. And the particle is this red dot here. This is the current sheet that is going to evolve. The red curve here is going to follow the Lorentz factor of the electron. The blue curve here is going to measure the Z component of the electric field, so out of field component of the electric field.
Feryal, just a warning, about 2 minutes left.
Okay, excellent, thank you.
Sorry.
So let me play this for you. And what you will see is the sudden jump in the Lorentz factor exactly at the same time as there's a non-ideal field appearing. And we've done this for, as I said, for many tracer particles. We've done tests where we removed, for example, the Q dot E from the acceleration terms. And what we showed is that the majority of the energization happens, the acceleration happens, when the electrons interact with these X points and the non-ideal electric fields in the islands, in the merging islands, and they quickly climb to these high Lorentz factors as a result. And how does this depend on the plasma parameters? So this is for a fixed sigma, changing the plasma beta. What you see here is that the higher beta values are softer, meaning they're, so pay more attention to the slope of these, so that, for example, the here red and the green and the blue have shallower slopes than the pink and the orange here. So when you look at what do I get beyond the peak, what you see is that the lower the beta value, the higher the acceleration, the more effectively they have been bumped up to high Lorentz factors. And that's actually not hard to understand, because the low beta simulations are also the ones where we see more X points and more plasmoid mergers, more small plasmoids forming and the subsequent mergers. So maybe Bart, you'll talk about the role of Fermi acceleration. I'm not sure if you will, but there's a small, you won't. Okay, no worries. But harder tails at low beta. How about the sigma dependence? What you see is, again, harder tails at high sigma. This is easy to understand. They're more relativistic to begin with, so they're easier to bump up to high energies. So we're basically, with efforts like these, moving towards a subgrid model for the energy distribution. By looking at the dissipation of MHD, we are trying to understand how the heating of these particles happen in the first place, by looking at actual acceleration mechanisms that we suspect should play a role based on all our simulations and understanding, such as magnetic reconnection. We're looking at how the non-thermal, how the additional acceleration happens. And by combining these, hopefully, we can now move towards GRMHD simulations that take into account a position dependence and plasma parameter dependent heating and acceleration. So studies like this as a function of sigma and beta, of course, they are simplified so that they can be used in larger simulations, but what is the power law index as a function of these plasma parameters, which can then be used, as I said, in GRMHD. I'll just show one last thing. Obviously, I don't have time to talk about it, but we love non-thermal particles. We love acceleration mechanisms. And this super fun observation from the gravity collaboration in 2018, where the flares that were happening in IR were spatially resolved, and gravity could actually track the motion of the centroid of emission as the flare proceeded. It turns out plasmoids in accretion flows resemble pretty well what a flare like that might look like, or can reproduce pretty well what a flare like that might look like. So this is the inner accretion flow. This is the position of the black hole. And simultaneously, when I play the movie, you're going to see if we inject a plasmoid and do the ray tracing to the observer at infinity, what the light curve and the position would look like. And because of combined effects of lensing and acceleration and cooling, you see that there are two images, but the centroid actually traces a teardrop that is pretty similar to what we see in that one spatially observed flare. So again, this in itself is a big parameter study, and more detailed work can be done as far as trying to fit it. But what we are trying to point out here is that you can get double peaked flares, you can get teardrop shapes, and more importantly, you can get these simultaneously. That resembles what the data do. So I will stop there and take questions.
Thank you, Feryal. I don't know if we clap in Zoom. I don't know. Do we? Yeah, let's try.
Thank you.
I guess nobody. Okay. So how should questions work? Should people raise their hand or just go?
Raise hands, chat, just go. I think anything is...
Yeah, okay. While people are...
I can't see the chat. Oh, okay. Maybe I can.
We'll monitor. Yeah, we can monitor the chat.
Okay. Yeah, so while people are thinking, you mentioned you guys did have a work with the guide field, right?
Yes.
So how did that affect things? Was it anything important, or was it mostly qualitatively the same?
So qualitatively, the presence of a guide field reduces the acceleration, the efficiency of the acceleration. So what we found is that a smaller fraction of the particles end up in this tail. So the power law indices are roughly similar, but the overall normalization of that power law, what we would model as a power law tail after the fact, the presence of that accelerated population of particles, the efficiency drops in the presence of a guide field.
And so we have...
And so when we do studies, again, based on GRMHD, of when we go to various places and ask in the simulations in the inner accretion flow and ask, where does this, excuse me, this is on silent, but it's beeping. Where we asked, what are the likely places of reconnection? Where does the phi field flip, etc.?
Yeah.
There is a distribution of guide field strengths, and that distribution is different between MAD and sane type simulations. So it is, more work needs to be done there, but perhaps what we will conclude is that particle acceleration is more efficient in one type of magnetic fields global configuration versus the other because of what the distribution of magnetic fields in those reconnection sites are like.
So I would guess that the MAD case would have a weaker relative transverse field or guide field. Is that true?
The MAD has,
just because the field tends to be more poloidal and less toroidal.
Yes, the MAD has a weaker. So I'm trying to remember.
So it would be more efficient in MAD.
Distributions of
yeah.
The out of fields component over B5. Yes, I think MAD is smaller overall.
Okay.
The strength of the guide field.
And then, so we do have a question on the chat. It says, is there any time scales associated with the generation of the plasmoids, or is it just a stochastic process?
So basically Alfvén time scales. So if I go back, I mean, it happens very quickly. So the first X point is at the moment of the collapse of the sheet. So when we triggered, of course, it's when we start the simulation. Let me escape this. Okay. It was here, I think. So these islands move. So the initial collapse is just the primary tearing mode time scale. So that's very, very quick. And the motion of these islands are set by is pretty close to the Alfvén velocity. They are pulled away from one another. And further interactions also happen on that time scale, which is the mergers of islands, further X point formation, further tearing, etc. all happen on a similar time scale.
And then we have a hand raised. I'm probably going to pronounce this wrong. Hike.
Yeah, that's correct. Do you hear me?
Yes.
Okay. Feryal, thanks for an excellent talk. I had a thing. Well, you mentioned we're moving towards really a subgrid models for MHD simulations. And I was curious, how much do we, maybe Bart will talk about this, how much do we actually lose by simulating in ideal MHD rather than non-ideal? Because I would imagine that in ideal MHD, all your dissipative and resistive scales are basically the same. That would mean on small scales, we basically do not, well, we under-resolve everything. So all the current sheets, small scale current sheets that could have been there are probably not there. And I was curious how much that really makes a difference and how much that adds up to the dissipation, or just overall your thoughts about that.
Yeah, certainly. So I was not advocating that direction as the only direction to go. By all means, we should do non-ideal MHD or kinetic simulations. Kinetic or gyrokinetic, where we integrate out the gyro motion and do a little bit of simplified kinetics. And those are going to capture these effects that you're talking about and non-ideal MHD. So I think maybe as a community, we will proceed in two directions. One is because observations are happening at this high rate and we want these parameter studies of what black hole variability can look like, images can look like, etc. At the very least, using these peak simulations to give us some guidance as if we're doing ideal MHD, what should we be doing, or how could we improve it? But at the same time, I'm absolutely not discouraging anyone from going in the non-ideal or kinetic direction. In fact, right now, we're working with with my current student and a couple people here on using Sgr A to do kinetic simulations. So a version of Sgr A that can handle massive particles and trying to see, but they're expensive. I mean, so that's why I think we're going to basically proceed in two directions.
Thank you.
Does anybody else have any questions? Oh, yep, Luca.
Hi, related question also to what Heike was asking actually is not only the accuracy of the model, like kinetic versus resistive MHD versus ideal MHD, but also the dimensionality of the system. Because that's very important. For example, when we look at these plasmoids, they are 2D structures that when you are in 3D, their lifetime can be significantly different. And also as well the possibility to capture and retain particle inside will be definitely different. And another difference will be the fact that you can have reconnection, let's say not just in the poloidal direction. It was a question also related before about the mad disk, but also you can have reconnection still anti-parallel, but with both poloidal and toroidal components. And I believe that this could be a significant effect because this is also an effect that can be captured also with MHD, but done in full 3D, because this has to do with the global, more like global physics of how you develop this and this dissipation region, more than detailed microphysics that is working inside the typical current sheet. So I was wondering if this can have a significant effect on the expected outcome.
Yeah, these are very valid points, and you made several of them. One is, what's the global structure of the flow? How well do we understand that? And the other thing you mentioned is even in the micro simulations, our dimensionality matters. So I don't know if I mentioned the particular ones that I'm showing you are what are called 2.5D. So it's on the XY plane, but the electromagnetic field vectors and the velocities are tracked in 3D, but the particle isn't allowed to. It's on the XY plane. So yes, and yes. So one of the other things that I will mention here is that how would reconnection happen in a real astrophysical system? So what we find are likely to, especially in the GRMHD simulations, what we find are thick current sheets. They're the natural time for the reconnection to develop there is long. So because of our resolution effects, because of how we're treating the plasma to begin with, one of the reasons we trigger is that we're saying it's unlikely that an entire multi-RG length current sheet is going to have reconnection triggered. It's going to go to the thinnest point, the closest approach where probably the velocity of the flow helps, and it's going to happen in a single place, as opposed to the whole current sheet is sitting there waiting for simultaneously to be reconnecting at multiple places. So yes, how we treat the global system matters, and it's going to affect our outcomes. And what we do, even in the high resolution, we're confining ourselves to understanding reconnection on a micro scale, the dimensionality will matter. It's not a solved problem. I'm just the messenger for what's the latest.
Okay, great. Thank you. So normally I would say thank Feryal again, but I guess we can all clap in silence.
Thank you.